is the most general way to set this one up? The normal, not turning your world upside down thought process. Integral. And we have a piece here that has a top and bottom. And we have a piece here that has a top and bottom. Agree?
How do you know it's only turn?
Well, look at the top and bottom of the black lines. You see how here it switches to a different top and bottom? So, to do this the standard way, I would have to integrate from here to here, which we'll have to go find where here is, get a calculator out.
This would be a calculator.
Yes, this is. We did another calculator problem on Friday. Calculators in polar mode, that's no good. What are the two functions that I'm graphing? Actually, three, but we'll pretend it was two. X cubed.
X plus 2 squared.
Good. The square root of x plus 2. And wouldn't you have to have a plus and a minus on that?
No.
Positive square root of x plus 2 and negative square root of x plus 2 to get that full parabola?
Is that like a break in the line, or is that just the graph on here?
It's just the graph. It's because it's graphing two different functions, so the calculator struggles with that. But at negative 2, they both equal 0. So they connect. I need that first intersection, which is actually the graph of negative square root of x plus 2 and the cubic intersection. Do y'all know how to do intersections when you have more than two functions? You use the up and down arrow to switch from function to function. It is -1, isn't it? So, my first integral will be from -2 to -1. The -2 I just did in my head, but if you needed to go find that, you could find where those hit the x-axis. Top minus bottom. What is the top and what is the bottom on the black part? It is almost the same thing. It's the square root of x plus 2 minus negative square root of x plus 2, which would be like plus square root of x plus 2. Or 2 square roots of x plus 2. You could imagine that you could have just done the top integral and doubled it if you'd thought about that. But
so this isn't the limit that's below the x-axis, it cancels.
It would if it were over here. Like if it were one function, but this is two different functions, and I'm finding the area between.
Okay.
Plus the integral from -1 to this intersection, and it's a decimal, isn't it?
Oh, I think I got the wrong one. Sorry.
I think several people did. You can go grab the correct one out of there, but don't worry about it. We'll get it like that.
Okay. Thank you.
You're welcome. We won't grade today.
Okay.
Probably that top piece of paper up there. Does anyone know this intersection? What is it?
1.214A623.
And remember, make sure you keep what she was reading is what you need to use. Now, I'm not going to write that down, but what she's reading is what you need to use. You need to use the stored decimal for that.
So you got the -2.
This one, the top is the positive square root of x plus 2, but the bottom is x cubed. You could type all of that in your calculator and it will give you an answer. Or you could be clever. What if you turned your head to the right again?
We always turn our head to the right.
Because positive would be on the right, farther
Or
right.
you could just turn your paper.
Okay, do that.
Turn your
Do it, look. What do you notice is always on the right? The cubic, which because if I'm going to turn my head, I have to do dy, right? So instead of x cubed, I have the cube root of y. Would you agree that's always the top? Minus the bottom. This one's already solved for y, isn't it? Y squared minus 2.
So if you turn your head, you're always going to do dy.
Yep.
But if you turn your head, we're not supposed to.
Well, it's always up to you.
It always works.
Yeah, it won't always be easier. It will always work. -1 was this bottom y value. Jameen, what was this top y value?
How'd you know that was the y?
When we found the intersection, Kelsey, when she read it to me, she said the intersection is -1, -1.
Oh, okay.
So I'm going to pick the y value. I don't know what the y value was on the other one, so Jameen's about to fill me in. What was it?
1.793.
So I do need y values. But would you agree this isn't easier?
So, so your y values, is it when your head is turned? So it flips the axis too, so...
Right. And that's why you're doing dy instead of dx, because your x is your y and your y is your x.
So when you plug it in, you just plug it in like x's.
Yep. You can type that in your calculator as x's, or you can use y, it doesn't matter. You know, in your calculator where you can do dy.
So you go from, when you turn your head, you go from the right to left.
Right minus left. And the reason you do right minus left is because the right is the positive part of the function, and the left is the negative part. So, very important note. If the area is bounded on the top and bottom, you can use the formula we've been using. However, if the area is easier bounded on the right and the left, then you can use a formula with dy. So I want to look at a few examples and make the decision which one would be easier. Another mental note I want to point out is you see how this equation, one of them was already solved for x? That's a good hint that maybe a dy is maybe easier, maybe not. Now, I made it sound like this was an option. There will be times you have to do it this way. Did y'all see some questions on the homework that you had to understand the right minus left notation? So there will be times you have options. Sorry, computer's going crazy. Okay, for each of the graphs, decide whether dy or dx would be a better choice. Top minus bottom or right minus left. Let's look at this one. What do you think? Dx, top minus bottom. Top's always y equals 1. The bottom's always cosine squared of x. And I sure wouldn't want to change it because then I'd have to solve for x and cosine squared of x, which would not be a fun solving. What about this one? Yes? Yes? Either way. The right is always on There's always a right, there's always a clear-cut left, there's always a clear-cut top, there's always a clear-cut bottom. So, either way, suppose whichever one you feel like. Now, because you see the equations x equals y cubed and x equals y squared, some of you may decide, hey, I'd rather do dy because it's already solved for y, I wouldn't have to solve the equation. I don't know what I mean by that. So, what about this one?
I would choose Y.
Definitely y. There's a right and there's a left. If you do dx, you'd have to split here, wouldn't you? Because the top and bottom are different at that split. So this one, you have to do dy. Because do you want to solve that for y? No. What about this one?
Top and bottom.
Good. Top minus bottom. I would do dx. Okay. Any questions about that? Okay. So that finishes up Friday's lesson. Now we're going to start today's lesson. We'll talk about that another time. Okay, so today we're going to find volumes of solids with known cross-sections. If you will, write this down, and I'm going to get some models out to show you what we're looking at. I'm going to add a word. Just another worksheet. And I suppose you have 2 nights to go, because I will not see you.
So that is official, right?
Yes. It was on the announcements on Friday.
Baseball. Hopefully it's rained out, so we play Wednesday at home.
I think ours already covered these.
Do it really? So hopefully ours does too.
So, yeah, the more, so,
Because and we haven't talked to go-karts.
Okay, this is what we're looking at. We're going to find the volume of a solid with a cross-section that's a shape that we know. So I have a square here. You can see kind of how that's working. There are a lot of solids that we know the cross-section for, like a cone. If you slice a cone, what's the cross-section? A circle, depending on how you slice it, of course. So we're going to be looking at volumes of solids with known cross-sections. I'm going to pass these models around so you can see them. Then I'm going to also draw on the board a little bit as well. So, remember that very first day we did integration? Remember the football example? And we learned that if we added up all the cross-sections of the football, we got the volume of the football. So we're revisiting that today. Well, the first thing I need to be able to do if I want to find volume is find the area of a cross-section. So step 1, you're going to write the formula for the area of a cross-section. This is the hardest part, is writing the formula for area. If the cross-section is perpendicular to the x-axis, you will integrate with respect to x. If the cross-section is perpendicular to the y-axis, you will integrate with respect to y, and I'll kind of show you why as we do an example. Using the given function, determine how to write the area formula in terms of x or y, and then using the correct limits, integrate the area to get volume. The cross-section is. Oh wait, which one? No, that was a triangle. It might be the wrong box. What?
So you've got like that.
A solid is made up so that at the base of the region between the x-axis and one arch of the curve is y equals 2 sine of x. Just for fun, I'm going to draw that. Would you agree that that's what y equals 2 sine of x looks like? The height's 2. And it's one arch of that. Each cross-section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. So we have a semicircle three-dimensionally coming out of this. And I know that you can't see that, so I have two ways I'm going to show you that. One is a three-dimensional picture down there. And two, I'm going to draw it on the board and show you a three-dimensional cutout.
Is this the stuff that, like, you said it takes, like, looking at shapes and stuff and guys, is that tendencies that are right?
No, that's what people say. Because I was good at it. I'm not. Okay, so we have bodily and aesthetic markers are better, I would say. Okay, so you see how this magnets are so we've got a shape where semicircles are going all along this, and it's pulling out a three-dimensional figure. So everyone kind of see what. No. So I want to find the volume. To do that, if I know the area of a cross-section, I can find the volume by adding up all those cross-sectional areas, which is integrating. So the first thing I need to do is, what is the area of a semicircle? 1/2 pi r squared. Everyone agree with that? That is the area of a semicircle. Well, on my picture, what is the radius? Half of the function, half of top minus bottom, which is just 2 sine of x minus 0. So 1 sine of x. So my radius is sine of x, because the height of this curve is 2 sine of x all the way across there. So my radius is just sine of x.
So the radius is accounting for every single x.
Yes. So the radius all the way across at any semicircle, see how they're different size semicircles?
So the radius is always going to be not just like a variable. Like
It will always have a variable in it, unless it's a horizontal line. Other than that, it would be changing. So my area function is 1/2 pi times sine of x squared. And I'm going to integrate that dx from 0 to pi, edge of your regions. So it started at 0, ended at pi, because that's where sine crosses the x-axis. Integrating that will give you the volume of that solid, because it adds up. The little dx stands for the little width. So if you look at those little pink cutouts I have up there, those are those foam things from like Hobby Lobby, you know what I'm talking about? If I turn them sideways, do they have some width? Teeny tiny width, right? So we're adding up the volumes of all of those semicircles. And that gives you, adding up the volumes, which gives you the volume of the solid. Okay, let's look at another example.
So we don't have to
Well, you would need to integrate it, but it would be a calculator problem because sine squared is not something that you can integrate by hand in Cal 1. You technically could do it in Cal 2. I don't think they'll put it on the BC exam, but you could use that power reducing identity. Okay, let's look at the next one. Find the volume of the solid whose base is the region between the curve 2 square root of sine of x and the x-axis on the interval 0 to pi. If the cross sections are squares perpendicular to the x-axis. Yeah, the hardest part of this is kind of visualizing what's going on. So, I am, and you'll have to excuse my artwork, but I am.
Some stuff.
It is. I mean, it's the thought process, and that's why this gives you a volume, is because you're at that. But we aren't going to go all the way back and actually do a Riemann sum. We'll use the integral to do the nasty work for us. Everyone kind of see how that works? This is the shape we're getting. A bunch of squares coming out of this thing. Step 1, find the area of a cross-section. Well, what is the area of a square? Base times height, but that has two variables in it, and I don't think I need to. Yeah, side squared. Yeah. Since base and height are the same on a square, it's just side times side or side squared. What is one side of one of those squares?
2 sine.
Do I have to half it on this one? Why did I have to half it on the other one? Because it was diameter, my formula called for radius. So it's every one you'll have to look at differently is a different shape. But this one is a side, so we just need the side. So I'm going to integrate side squared.
I know the side is 2
This distance here. What is that distance? Well, this curve is sine of 2x minus 0 if you wanted to think of it that way, since we just got off of the top minus bottom thing. But this distance here is that y value, the height of the curve. And that y value happens to be 2 square root of sine.
I thought that was like the whole thing.
Okay, so what's the height right here? How could I find that y value right here? I don't know. Maybe it's 1. Maybe it's 0.9. Do you see what I mean? How could I determine it? Plug in that x value into this. Do you see what I mean? So the height anywhere along here is determined by this y equals function. From 0 to pi. I'm going to add up all those areas of squares. This one I could do by hand. Why could I do this one by hand and not the last one? It's just for sine of x. The other one had sine squared, and that is a very complicated integral. So I'm going to go ahead and do this one by hand. What is the antiderivative of sine of x? Negative cosine. The other one we would type in our calculator. I didn't, but you would. Cosine of pi is negative 1. Cosine of 0 is 1. So 8 And that would be cubic units, whatever the units were. It didn't tell me, but that would be cubic units. I think it, yeah. Because it is a volume. It's the volume of that shape. We're going to do several with the same picture. So look at this one. Go ahead and write the problem down. While you're writing this, I do want to tell you this is a useful thing in the real world. My husband had a friend who worked in construction, and he was bidding a job, and he had me find the volume of something to see how much concrete he needed to fill those big statues and things out in the front of malls and stuff. He needed to know how much concrete he needed, and it was kind of an elliptical type shape. And he needed the volume, and so we were able to get really close using the cross-sectional radius so he could get a more accurate bid. The standard way to bid those on a job is to just make it a rectangle or make it a cylinder and guess, overestimate. So he was able to really know exactly how much it was going to cost him to get that much concrete. So, useful in the real world, I suppose. That's the only time I've ever used it. But I also don't really work in the real world. I'm just Okay, so we're going to work these one by one. The first one is squares. So we already know what's the area of a square. Side squared. And we're making squares. What is the side of one of those squares? I have to do a top minus bottom thing here, don't I, to get that side length? So it would be the square root of x minus x squared. So the side would be the square root of x minus x squared. So I'm going to do the integral. Square root of x minus x squared squared. Can I just square both of those pieces? No, I would need to FOIL, which you could do, but for now I'm just going to set up, just for time purposes. I believe those intersections are 0 and 1. How could we find that? Set those equal to each other, square both sides, you'd have x to the 4th equals x, is that right? And you do get 0 and 1. Okay. Next one is different than we have seen so far, and it asks me to make the cut perpendicular to the y-axis. So instead of an up and down, this isosceles right triangle is going this way. Now what that changes is my cuts are now dy's. So if I am perpendicular to the y-axis, I have to do dy. Because my little widths of those triangles are now dy's to multiply by the little width. So I have no choice. I have to use a right minus left thought process, which is not a huge deal. Side note, what is the area of an isosceles right triangle? One half base times height. If it truly is isosceles, what do you know about the base and the height? So 1/2 base squared if it's isosceles because the two legs are the same width or the same height.
Please excuse the interruption. I need the following students in the high school office: Chris Brown, Kaylee Holiday, Cheyenne Horton, Darian Simmons, Gillian Bloomington, Paige Cole, and Sydney Williamson in the high school office. Thank you.
I will have to use y values. So I need to go back up to my original. And solve. I do get plus or minus the square root of y, but would you agree this is the positive half? So it's just the square root of y. So right would be the square root of y. Left would be y squared. So that will give me this distance, this base. And then I need to integrate from y values. I want to point out this looks like my limits aren't changing because they're not. But remember this time I'm now using 0 to 1 on y, not 0 to 1 on x. Does everyone know what I mean by that? So if the y's had been different, those limits would change.
So there's no, like, we don't have to, since there's not, like, two variables, we don't have to find a side or something, or, because, like, on first, like, on area ground squares in the semicircle, we have to find the side in the bar.
We had to find the b.
So, oh, that's just the square root of y minus, okay.
So very similar. In fact, if these had been squares instead of triangles, the only difference would be we wouldn't have the 1/2 in front. So different shapes don't make this hard. The hardest part is figuring out what that length is, really. It's probably the hard part. Perpendicular to the y-axis again, except this time I am semicircles. What's the area of a semicircle? 1/2 pi r squared. So what's the thing I need to figure out? What is r? Since I'm perpendicular to the y-axis, I have to do dy. I don't have a choice. Very good. So I have 1/2 pi r squared. And the r is, yes, half of that distance, right? So you could either divide by 2 there or put a half in front. It doesn't matter. But the half does have to be in the square, right? It has to be inside because it's part of the radius. I'm going to go back to perpendicular to x next time. Am I going too fast? This time I'm making rectangles perpendicular to the x-axis. What's the area of a rectangle? Base times height, length times height. Very good. Which could be a problem because that's more than one variable. That could be problematic. We'll see.
This one's to the x.
Yes, and why is it x? I'm cutting these cross sections perpendicular to the x-axis. So what is the base? Square root of x minus x squared. Does everyone agree with that? It's that distance. That's the base. What is the height? 4 times that. How do you know? Who tells you that? I'm just going to put times 4 there. Oh, sorry.
Wait, can you do that? Or you just do the square root of 4?
In other words, what I really did is I kind of rewrote this to say, well, this is the same as base times 4. Or you could have done base squared times 4. You've got options. Any questions about that one? All right, that's where we stop today. Your homework is a worksheet on volumes. kind of solid, so you don't cross.
Discuss corrections too.
I gave the test back on Friday. So there it is. So if you, this homework is not very long. You do have an extra evening that you're not used to having because you have Tuesday off as well. So if you want to work on test corrections on your day off, it would be a bad idea. This is like I said, pretty short worksheet. Nothing crazy.